All right. Good morning, everyone. Looks like it's 10 o'clock. We have a lot to go over today, so we might as well get started. Um, good morning. I'm Matt Stevenson from Sunstone Circuits. Um, I'll be your guide today on our PCB 101 journey. Let's see. We've got a full agenda today, so we will be answering questions through the Q&A section in the Zoom chat. We'll try and get to some of those midstream, but if there's time at the end, we'll try and also get to some of those at that point. So if you have any questions, go ahead and use your Q&A section in the Zoom. All right. So here we go. The Sunstone and American Standard Circuits are both US-based manufacturing facilities. Sunstone is based out of Malino, Oregon, and we've been building boards here in this facility since 1972. So if you do the math, that's about 52 years. And then American Standard Circuits is based out of West Chicago, Illinois, and they've been building boards since the late 80s. So between the two companies, we have quite a vast amount of experience building boards, and want to continue that through the next 50 years. So today our topic is PCB 101. So we're gonna go through the data requirements, some information on material and stack ups, some of the cost drivers and design drivers, and then we're going to go through the manufacturing process from the beginning, pretty much through the end. There's quite a few slides and quite a few photos, etc. So hopefully everybody will have something they can take away and learn something today. But again, if you have any questions, please put those into the Q&A section on the Zoom. So again, I'm Matt Stevenson. I'm the general manager here at Sunstone Circuits, which was acquired by American Standard Circuits almost exactly a year ago. We will be doing our 1-year anniversary here in about 2 weeks. So pretty exciting news in the first year of our mutual partnership. All right, so diving in, PCB 101, we're going to be, like I said, we're going to be going through a lot of the general PCB manufacturing process, as well as some of the other things associated with that, design, layout, etc. One of the things we like to stress in a lot of our general communications is, communication with the PCB manufacturer ahead of the finalizing the design is always a good thing to make sure that you're able to get the design you want built with the the reliability and everything that you need, and that there aren't any gotchas from the PCB manufacturer once you submit your files. So always keeping that dialogue up to date during the manufacturing process and even before during the design process is a great idea, especially if you're using some of the cutting edge technologies. All right, so for PCB manufacturing, we require electronic data to get the manufacturing process started. Some of the CAD data that we like to see, ODB++ has been one of our favorite choices over the years, and Gerber 274 data as well. That's kind of the gold standard, has been in place for a lot of years, with the ODB++ being kind of the newcomer on the block. Sunstone also has several of the native CAD files that we can just take directly from you, Eagle and Altium, Cadence. So you can upload those files directly, and then we can create the necessary Gerber files from those and get your manufacturing process started. Also, DXF files from like an AutoCAD type of file also work. They do require a little bit more work on the CAD side CAM side to get the files into a format that'll work, but are acceptable for sending as well. We also ask that you send fab drawings, stack up information, any other data on your print sheet, etc. Your that you need for your manufacturing, tolerances, non-standard specifications, README file with any notes that you want us to read or see. Is always a great place to see that. So at Sunstone, we have our pre-engineering part of our CAM. So the files come to us. Our pre-engineering group, they go through the files, and they're basically making sure that the files that you submitted, that the order form that you submitted, and the prints, etc., are all kind of in sync. If there's any discrepancies between the two, we will at least ask the question to make sure that we are manufacturing exactly what you require, what you intend. So they review the material. If there's impedance requirements, they look at the modeling of it there to make sure that the materials and the traces and the stack up are going to work for your impedance requirements. They help define the shop floor process sequence and the travelers. They also are looking at any customer specific requirements. Sunstone has a pretty vast list of customer, what we call specifications that are specific to a customer and what they may need. So those we take into account as well with the data. Then the files go over to our CAM team, and they start doing the actual tooling of it. So they'll do any minor edits on the files, teardrops, solder mask swells or shrinkages to make sure that the dams are wide enough, that the traces and spaces are good. They'll add copper thieving as requested and allowed. They'll do the stepping, if it's going to be V-score or tab with perfs, they'll do that as well. They'll export all of the files, the drilling files, the route files, any of the copper layers and solder mask files. So those all get exported, and then they'll print the hard copy of the traveler, and then that goes down into to the manufacturing department. A couple of things that we want to make sure that we pass on to you are some of the things with materials and stack ups. There's lots of different dielectric materials that are available. Sunstone primarily uses an FR4 material, but American Standard, who you can get quotes and orders directly through Sunstone for American Standard, or going directly through the support team at American Standard, can get the other polyimide materials, high-speed materials, flex materials, embedded resistors, metal backs. All of that good stuff is available with them. Sunstone, we publish all of what we consider our standard stack ups on our website. I've put a link to it here in the presentation, but we have all of our, 4-layer, 6-layer, 8-layer, 10-layer, 12-layer, 14-layer, depending on the copper weights, et cetera, that you're looking for. We have those all posted on our website. And so if you want to do your impedance modeling up front, you have the dielectric constants as well as the thicknesses, et cetera, that go through with those to help with your design phase. We also have the non-standard stack-ups available. So if you have a very specific stack-up that you need, we're able to accommodate those both at Sunstone and American Standard. One of the things that helps with material availability as well as cost are using standard slash sheet designators for material rather than calling out a specific brand of material. It allows a little bit more flexibility when you have the flexibility to do it with something a little more general than specifying, say, for example, 370 HR. If you do the /126 That actually helps a little bit in terms of getting materials in and out. Question, what does the slash sheet mean? I'll go ahead and answer that one in line here. We are, there's a spec, an IPC spec 4101, and they have a grouping of materials that have specific resin types, glass types, as well as mechanical and electrical properties that they group together, and they call it like a slash sheet. So there's a grouping of, like I mentioned, slash 126 is a grouping of like FR4 materials that have similar characteristics to them. And if you're able to be a little bit flexible, it opens up a variety of materials rather than just a specific material. So refer to that IPC 4101 spec, and that'll give you all the information you need on slash sheets. Also using standard material thicknesses also improve the availability and cost for you on your end. So like 2 mil, 5 mil, 10 mil, 18 mil, 35 mil, these are all some of the standard material thicknesses. So anytime you're able to use those in your design, obviously the better is going to be for the availability, etc. All right, so with a lot of the stack ups, symmetry and balance is really one of the keys to keeping the parts from being as flat as possible and working as well as possible. So you can see in this example, there's two ways to get this stack up. One is a kind of a 4-layer design with a lot of pre-preg between layers 1 and 2, a large core, the blue color, between 2 and 3, and then a small amount of pre-preg there between layers 4 and 5. The same design built as a kind of as a 6-layer, if you will, an 8-layer with 3 cores and pre-preg and a couple blank copper layers in there, keeps the thicknesses balanced, so there'll be less opportunity for warp down the road. You'll get a better result overall than you would if you use the stack up on the left. So really, that's one of the things that we like to encourage is keeping everything as balanced as possible. Obviously, sometimes there'll be need for some imbalance or some unsymmetry, but balance in the material types that you're using. If you're using mixed packages, the copper weights, trying to keep the 2 ounce symmetrical with the 1/2 ounce or the 1 ounce on those internal layers, and then also the laminate thicknesses as well as the pre-preg thicknesses. So balance and symmetry. All right, so moving on, some of the upfront design and cost considerations that we'll kind of talk through here. So we got these kind of broken down into how much they're going to impact a cost based on the thing that's going on there. So some of the low items are just complex routing and scoring, thinner and thicker PCBs. Obviously the thinner and thicker, they have handling considerations in the manufacturing area. So they make them, heavier, harder to handle, or they're thin and flexible, plus the different amounts of material that go into there, as well as solder mask via plugging. Again, it's an adder, but not a big one. We go to the medium adders, and this is where we start, seeing some of the higher prices, but very dense drilled designs. When you start looking at 20,000, 30,000 vias on one board, the processing time to drill it really takes quite a bit of time and adds cost to the overall design. Stitching vias are a great example of one use of a lot of vias that typically do tend to take a lot of time on the drill machine. The hole diameter, when you're looking at your overall smallest holes, obviously the smaller the hole, the lower the stack height, so the less of the boards we're able to drill at the same time. The aspect ratio and the considerations going through plating and through some of the other processes, via plug, et cetera, become more challenging the higher that aspect ratio goes. So anytime you're able to use a larger via, it helps with cost, reliability, and overall yield on your product. Castellated holes also, sometimes they're definitely necessary, but they add several, manufacturing steps and drive up the cost a little bit as well. So some of the high cost adders, obviously there's a need for these at times, but layer counts above 20, mixed materials, etc. If you have a lot of requirements that require coupons to be part of that, mil spec requirements, impedance, we're able to get less actual functional PCBs onto a panel because we're having to build the coupons as well that take up that real estate. Expensive materials, high frequency and low loss, those can add significantly to cost. Embedded passives or resistors or capacitors add to that in terms of processing as well as material cost. Blind and buried vias with multiple lamination cycles are higher cost adders. Plugged holes with epoxy, conductive and non-conductive. So there's a lot of additional steps and stuff that go on with those. And then like selective plating thicknesses, if you need to have multiple different surface finishes on the same panel, again, requires multiple manufacturing sequences through the same type of sections. So obviously some of these need to happen to make your designs, but anytime you can limit those or eliminate those from your design, if you're cost sensitive, the better overall cost will be. So moving on. So talking about manufacturing panels, I mentioned this a little bit. But anytime we have to add coupons to a design, it limits our ability to put actual functional circuit boards on there. The example that we have here, you see you've got two big boards on there with a few coupons to the side. Honestly, we wouldn't be able to get a third panel up without those coupons, but on smaller boards, that's definitely a cost driver. So anytime you can eliminate the need for coupons, the better the cost will be as well. Obviously, sometimes you need those coupons. All right, so design considerations for reliability. So when you do your stack up in your design, there's a couple things to be to take into consideration with your the planes and the layer to layer retained copper. If you have multiple layers, and usually this happens with higher layer count boards, sometimes it can happen on 4 and 6 layers, but usually it's in the higher layer count boards. But anytime that you're either stacking copper in a specific area on every layer or eliminating copper on every layer in a specific area, it can create issues of either low pressure or high pressure during the lamination cycles. And these can tend to create voids of the epoxy or resin-rich areas without glass to reinforce it that can cause issues with delamination or decay variation, just based on whether it's resin-rich or resin-starved. Sometimes the adhesion, especially if you've got a lot of copper stacked together and you're squeezing out a lot of resin into other areas of the panel, you can actually get areas where the adhesion isn't as good because you're trying to adhere glass to, say, copper or copper to copper in some areas, and don't really get the good adhesion of the epoxy. So trying to keep, again, balanced and symmetrical. So in Gerber data, here's a couple examples. The one on the left is a area that has the big black area is void of copper. So in order to kind of fix that, you can see what they did on the right here is they added a split plane with retaining copper in that area to kind of eliminate that low pressure area. That type of design on one layer is probably not going to be catastrophic. Probably isn't going to create too many problems, but if you stack that up, 2 or 3 layers on your 8-layer design, that could definitely create some issues with a low pressure area. Adding external thieving, especially on the external layers, also helps with plating, creates more even copper distribution. If you add, like 50 mil dots or squares, they recommend on about 75 mil centers. It's not necessarily electrically active, but it does help with the distribution of electroplating. A lot of times, if that's added, that'll get added by our cam toolers as well. But having that on internal layers also helps with that resin distribution a little more than just bare laminate would. All right, so electroplating. So here's an example of electroplating and how different designs can impact signal integrity. So if you look at, so we use a photoresist as our plating mask, and we plate in the channels of those of the photoresist there, and those will become your functional copper features, your traces, your pads, through holes, etc. If the copper isn't evenly distributed, or we have areas of what we call high current density because of the amount of copper in a area, we can get variations in height of that copper. So this example, we've got a lot of traces that we're plating on the left side of that board and not a lot on the right side. So if you think of it from a physics standpoint, there's more current per square inch going through these traces on the right-hand side of the board as opposed to the left, where it's a little more distributed. So as you can see in the middle row there, we get copper height that's about halfway up the photoresist on the left side and over the top of the photoresist on the right side, because we're plating that faster due to the current density. So what you see is you actually get variations in height of those copper. And, if you're thinking it from like an impedance standpoint, where the cross-sectional area of that trace is important for overall electrical impedance factors, you can see the traces on the right have significantly more cross-sectional area to them because of the mushroom on the top, as well as the overall height of those traces compared to those on the left. So especially when you have impedance requirements, trying to keep those, keep the copper area kind of nominal around them, add thieving or, planes around them, that tends to help make those traces a little more even and better performing in your impedance type of designs. All right, so that's kind of some of the design considerations we want to talk about. Now we're going to kind of get into the nuts and bolts of actually manufacturing of circuit boards. So the manufacturing process is lengthy. There's about 21 steps here indicated in this particular process flow, and this is just a fairly simple single lamination board without any via filling or anything like that. So this is a pretty standard board that Sunstone's probably going to be able to build relatively quickly for you. But this process has 21 steps to it. If you start adding sequential lamination, via fill, etc., because of HDI concerns, this number of steps can balloon to 30, 40, 50 pretty quickly, which is one of the things that influence the overall cost, complexity, reliability, etc., those type of designs. So if we look at a board kind of in macro, at the end of the day, you're going to want your board with your assembled components on it, right? That's the end goal. We look at the outer layers, which is what we call the like layers 1 and layer N. And then the internal layers is everything in the middle there, 2 through N-1. So when we talk about inner layers, outer layers, and components, that's what we're talking about. Drilled holes, they come in a variety of holes. The one on the left there is more of a blind hole. Looks like it goes between layers 1 and 3. And then you've got a through hole drilled there on the right side, all the way through, connecting through every layer. Some have clearances, some have connections, but it definitely goes through all the layers there. Okay, so really the first step in the actual manufacturing, once CAM has done all of their tweaks to the data, output all the files, created the traveler, the first step is we are going to create the internal layers. So say for this example, we have an 8-layer board that we're going to build. We build them in pairs of copper-clad laminates. So in general, in a balanced and evenly distributed 8-layer design, we're going to build layers 2 and 3 as a pair, 4 and 5 as a pair, 6 and 7 as a pair. So we're going to get 3 pairs of inner layers that are going to get built and then brought back together and laminated together. So the first step to that is we take this core material, copper-clad laminate, that it has copper on both sides of the right thickness, whether that's 1/2 ounce, 1 ounce, 2 ounce, 3 ounce, 10 ounce, whatever that might be. Layer 2 and layer 3 are commonly the same thickness, but can be different depending on designs. But we take these panels that are copper, laminate, copper. We apply a photoresist to both sides of it, which is a photosensitive polymer. And what we're going to do is we're going to image that with our LDI in this case. So to that photoresist, we're going to run it through the imaging process, the LDI, which has, it's basically a glorified laser jet printer. So it's going to expose the film in specific spots where we want the resist to stay long term. For an inner layer, that will be the parts that we want to keep as traces and connections on those internal layers. The parts that are going to be unexposed by that LDI, we're going to wash away, develop away, and that will act as our etch mask for that inner layer. So you can see that this particular design, we have our photoresist, we have our copper foil, we've got voids now in our photoresist where we developed it away. And then what we do is we go through and we develop that resist and remove parts of it. So we're left with the top and bottom. The parts that are in blue is our etch resist, our photoresist. And then the parts that are black on top and bottom are going to be the absence of that, which exposes the copper below it to our etching process. So that once they get developed, they run through the process there. You can see at the panel at the top, kind of an example of what I'm talking about. You've got the copper below that's exposed, and you've got the photoresist that's protecting parts of the image. For an inner layer, obviously those are going to be what we want maintain on the board. All right, so then we go through and etch. So we expose that panel now to an etching solution. Two common ones are cupric chloride or an ammoniacal etchant. There's pluses and minuses to both. Usually with inner layers, the cupric chloride gives you a little bit better etch factor and a little bit straighter sidewalls. But in general, as you're etching down from the top down, the top of the trace underneath the photoresist will be exposed to that etching material a little bit longer than the bottom of the trace. So in general, you'll get kind of a trapezoidal shape to your etched traces. There are some things with chemistry and temperature that can help mitigate that a little bit, but in general, you're going to get kind of a trapezoidal shape to your traces, usually less pronounced on inner layers than outer layers. Okay. There's an example of a panel with the copper etched away now. That is kind of a higher speed material, so it's kind of a white colored laminate as opposed to a yellow for FR4. But that's what you're seeing there is the laminate and the photoresist. All right, so the next step, we got to get rid of that photoresist. It doesn't do us any good in the manufacturing process once we've used it as an etch mask. So chemically, we run those panels through our resist stripper, and it chemically removes that photoresist now from the panel. So we're going to get basically just a panel now. Copper and laminate are the only things on that panel. So both sides get processed at the same time. Both sides get etched at the same time. The resist strip happens at the same time on both sides. So that pair goes, and it is now basically that internal layer, those cores, and it's going to go to the next step, which happens to be an inspection step. Whether you're using AOIs or some other way of inspecting it, we're going to look at the copper that's retained on that layer and make sure that all of the signals have continuity end to end, and that the isolations are all in place. So we're going to utilize the electronic data that we created from the tooled files, and we compare on a pixel by pixel basis the retained copper on the panel to what that electronic data looks like. And anytime there's a discrepancy on a pixelated basis, that shows up as a potential defect that either gets addressed, scrapped, or repaired, or sometimes even lint or debris shows up at this point, and it's able to be removed and shown to be good product. All right, post-etch punch. So we need to align all of these layers together in order to get, layer 2, layer 3, 4, 5, 6, and 7 all aligned as close to possible, so that we're gonna, be able to get the through holes through and everything aligned just right. So we use what we call a post-etch punch. There's targets on every layer, and it goes into this machine, and it looks for the true center as best as possible of both sides, all 4 edges of that panel. So you're talking 8 different points that it's looking at, trying to get the best true center of those 8 points, and then punches in our tooling holes that will be used during lamination. Usually the registration tolerance on this type of equipment is pretty tight, and we're able to get pretty good layer to layer to layer registration. You can see along the centers of all 4 sides there, that kind of blue oval, that will be the hole that we're punching with this piece of equipment. In order to get good adhesion of these copper layers during lamination, we have to run it through a chemical process, an oxide or alternative oxide process that roughens up the surface of that copper. and makes it more prone to adhering to the epoxy during the lamination process. So this will be what our core looks like. We're going to go ahead and put this oxide coating on it, and you can see we've added a blue layer to the top of the copper, which is basically that adhesion promoter. All right. Now we have all of our inner layers are manufactured. They've run through the oxide process. Now the next step is putting them all together into that manufacturing panel. So we do that in what we call books. It's basically a steel plate that has pins on the four edges that coincide with the holes that we punched at the post-etch punch process. And then it goes in a specific order. Your traveler will have your stack up and your, basically your requirements for what this layup looks like. So it'll tell you what thickness copper needs to be on the foil layer, what pre-preg layers constitute the between like layer 7 and 8 here, for example, which core goes on, how it's oriented, and then you get pre-preg in the next opening, your next core, pre-preg core, pre-preg foil. So we'll stack these up as they will show up in the final design that has been designated by the stack up, either that you provided or the standard stack up. And then once you have your book complete, which is generally several panels thick, separated by a Teflon release sheet, we're able to go actually into the press where there's heat and vacuum applied to the heat pressure and vacuum applied to the book. It gels the epoxy in the pre-preg layers, liquefies it a little bit. It's able to flow and fill in the gaps. And this is where those low pressure and high pressure areas that we talked about earlier come into play. But this epoxy then, flows, fills in all the gaps. As we ramp the temperature, there's a required dwell time at that specific temperature. Every material behaves a little bit differently. Every press is a little bit different. There's different heat lagging, etc. So understanding, your individual press and your press profile is pretty important to be able to get this process dialed in and manufactured properly. So we're applying that heat and pressure, and it dwells in there for a period of time. And then after that, that heat excursion happens, and the panels are starting to cool down at a controlled rate, that those pre-preg layers that we put in there are now basically the same epoxy makeup as the cores were. So it's what we call C stage of that cycle. And it's all cured and hardened and adhered to the copper via the oxide layer. And everything at this point is really solid and well done. Things do change during the pressing profile. Things expand, copper expands, the cores expand a little bit with those kind of heat. So there is some, shrinkage or growth that can happen during this process. So as a manufacturer, knowing your material and how they behave during your press profiles are the key to adding some kind of scaling factor in there, so that once the press process is done and it's cooled, all those layers still align the way that we expect them to. All right, so now we have a manufacturing panel that is 8 layers thick. It's copper on top and bottom, and you've got your 6 layers internal. We're going to drill the through holes through that part. So the panels go over to the drill department, and they do a test on some coupons, usually some registration coupons, to ensure that the drilled holes are hitting all of the internal layers like we'd expect before we actually drill the images. Once we verify that the registration to those internal layers is good, we drill the panels there. You can see in this representation of a drill bit going through the panel that we're drilling, 25% further than the actual bottom of the panel. This is done into a phenolic material or another harder material on purpose to get a good, solid, smooth drilled hole. I'm sure most people have seen drilling a hole into a 2x4, and if you don't have anything behind that 2x4, when you exit, it tends to splinter and volcano out that hole on the backside. Same is true with circuit boards. So having a hard phenolic layer there at the bottom allows us to get that nice smooth drilled hole all the way through the part. And that's what we're looking at there is drilled holes now on the copper layer, which is going to be layer 1 in our case. All right, so during that drilling process, drilling has friction and creates heat, and epoxy is kind of a plastic, and it tends to melt under heat a little bit. So what happens is you get a smear of that resin as you're drilling through the process. It tends to coat your internal connections and is not going to create a robust connection between your through hole and your internal post. So either a chemical process or a plasma process is employed at this part to dissolve that melted epoxy over the internal layer posts. Does a great job. It creates your etch back if needed, etc. So that's what it looked like before and after. So you can see before you've got kind of a messy look to your copper post. And then after the desmear process, it looks nice and clean. You can see your copper, you can see your glass fibers, and you can see your epoxy in there. So that creates a nice, clean hole ready for copper deposition. The first part of that process is what we call an electrolysis copper deposition, which is a catalyzed reaction. That's whole job is to put a thin, somewhere in the neighborhood of 25 to 50 microinches of copper inside of those holes, whether it be a blind via or a through hole. And that is just going to be sufficient amount of copper to accommodate the electroplating of copper down the road. So this chemical process, it makes sure that all the copper surface is clean, and then it puts this small amount of copper into the holes. Now we're going to go back through the image process one more time, and we're going to put those outer layers on. This time, the polarity of the image is the exact opposite. We are going to use the photoresist rather than as an etch mask. We're going to use it as a plating mask. So we want to expose the copper below it to the areas that we actually want to keep on the panel. And we're going to increase the thickness of those through electroplating. So all of the traces are going to be exposed to the copper below it. All of the pads, the surface mount pads, the through hole pads, etc., are all going to be exposed at this point. And all of the copper we wish to remove to create those traces and pads, etc., is going to be covered by the photoresist that we're going to etch away later. So we use the same process, an LDI or a high intensity light source to create those traces and pads. Again, we're going to develop off the photoresist that we don't want to expose the traces that we do want to keep. So it's looking similar to this, the purple part of it being the photoresist, and then the through hole surface mount pads, etc. Any etched text, etc., are all exposed right now. Okay. copper plating, we're going to electroplate all of those exposed areas. We're going to add approximately a mil of copper to the center of the holes, depending on what class, and we're going to beef up those copper. I'm going to speed up a little bit here because we got about 15 minutes left and a lot of processes left to go. So, all right, so after the copper plate, we electroplate a little bit of tin onto the surface of all of that copper, and this metal is going to act as our etch resist through our etching process in the next step. So before we use photoresist, now we're going to use tin as an etch resist. Okay, so we got tin plated on top of our copper through holes and pads. We're going to strip off our photoresist at this point, exposing the copper below it that we want to remove. Okay, there's our exposed copper and our tin. Goes through the etching process, basically the same as I talked about before. Generally, an ammoniacal etch is used for an outer layers. And we are going to etch down to the laminate, creating those pads and traces, isolating where we need to. The next step we do, so okay, here's kind of a cross-section view of what we see. There's our laminate, our base copper, our thin layer of electroless copper, and then our plated copper with the tin on top of it. After it goes through etch, you can kind of see the sidewalls have that curved kind of trapezoidal curved look to them, which is the effect of the etching. The thicker the copper layer, the more pronounced this undercut of the etch resist is. So you can see as we increase that copper thickness, we change the shape and the size of that trace. All right, so now we want to strip off that tin layer and expose the copper below it. So we run through a chemical process that's really nitric acid based, and it removes that tin without attacking very much on the copper layers. So now we have our board. At this point, we have a fully functional circuit board. It's got all of your traces defined, all of your isolations and continuities are all defined. We just need to go through the last couple processes to make it acceptable for assembly and shelf life, stability, etc. So again, we inspect the parts through the AOI process, comparing what we've got retained versus what the electronic data suggests. All right, we're going to apply solder mask. So this is the green stuff that is most commonly identified with circuit boards. This is kind of the Teflon layer that allows solder to go only where you want it to go on your solderable surfaces, and the solder mask acts as basically a Teflon that the solder just falls right off of. So we're going to apply that solder mask layer to the external layers. We flood coat it over everything. So all of the copper solderable features are covered at this point, but then we go through an exposure process again, very similar to we have at the inner layers and the outer layers stage. And we are going to develop off solder mask and expose those solderable surfaces. All right, so we can see some of the via holes are still covered with solder mask by design. But our solderable features, our pads and through holes, etc., are now void of the solder mask layer. Silk screen's applied at this point. Most of the industry uses a glorified inkjet printer to apply the silk screen. It registers to some fiducials on the panel, aligns the electronic data to the physical panel, and then goes through and does an inkjet representation of that silk screen onto the panel. So you can see in the digital image there, the red layer is the solder mask layer. So it's adding our reference designators and component outlines, etc. Any logos or whatnot that you have on your panel. And it basically then looks like this. This is a finished board. You can see the pads are actually Enig, but you can see the white silkscreen being applied to that board. After silkscreen, we apply our surface finish. For the most part, there's a couple, like electrolytic hard or soft gold actually gets done prior to solder mask addition, but the rest of these surface finishes are done after the solder mask and silkscreen are done there. So you got Enig, you've got immersion silver, electrolytic hard or soft gold, OSP, solder, whether that be lead-free or leaded, hot oil reflow, which again is done before solder mask, immersion tin, and Enipig are some of the most popular surface finishes available. All right, once that surface finish is done, we're basically able to singulate out our boards, whether that be into an array or into a single image. So we add any non-plated holes, route any cutouts or slots at this point that are non-plated, and then singulate the boards into their correct array. There's one, for example. Electrical test, boards get tested. You know, a lot of volume orders get done through clamshell or bedded nails. Sunstone, we don't use that anymore. We got rid of that process a number of years ago, and everything goes through a flying probe process where we're checking for continuity and isolation. Boards are inspected and getting ready to be bought off for a clean bill of health. We utilize the APC A600 as that visual standard, as well as cross sections, et cetera, based on 6012 or 6018, depending on your design. Verification, whether there's impedance testing or anything else that's done, CMM verification of the tolerances and the dimensions are done there as well. Cross sections, where required, are done as well, so we can see what the internal part of the board looks like, the copper thickness inside the holes, whether there's any laminate voids after reflow. Just basically looking at the integrity of the holes in that coupon to make sure that things are acting as they should, and that the boards that we're going to ship meet the various requirements of IPC and the customer specs. Boards are then packaged and shrunk wrapped, etc. We add humidity sensors as well as desiccants into the package, usually for storage, and the boards are shipped and sent to you or to your assembly house, wherever you need them shipped. As a reminder, Sunstone and ASC have a variety of different webinars, books, blogs. We offer an online DFM as well that can help with any of your design questions, etc. So there's a lot of information on the American Standard Circuits website, as well as the Sunstone website, to help with a lot of the content in this webinar, as well as other higher capability or needs that you might have. Ultra HDI, HDI, thermal management, etc. As a reminder, capabilities are pretty diverse: flex, rigid flex, digital PCBs up to 34 layers, different high-speed materials, heat sinks, embedded copper coins, IM PCBs, etc. So that's kind of a little overview of circuit board manufacturing. So let's see, we got about 5 minutes, so I'm going to go through a couple of these questions here. All right, one of the first questions: the advantage of core construction against a foil construction. So from a manufacturing standpoint, a foil construction is kind of the gold standard, the standard process of that. When you add a core construction, You're basically laminating cores on the top and the bottom, rather than pre-preg in a foil. So what happens is you have to etch that layer 2 and layer N-1 while keeping the copper on layers 1 and N. So it's a little bit of a deviation from the process, but it's very feasible, and it keeps that thickness very constant between layers 1 and 2 and N and N-1. If you have impedance requirements, etc., it makes that process really solid for the overall thickness between the 2 layers. But it does add a little bit of a manufacturing wrinkle. Nothing too exciting, very, very known, but definitely something a little bit different. Do you have preferred stackups you can import into Altium? I don't think they're importable as is, but I think they can be added one way or another into the Altium programs. Let's see. Can you do 2 or more different colors of silkscreen? Yes, it's possible. We can do that. Again, it's an added process step, but it is possible to do multiple colors of silkscreen. Even solder mask, if you really want to. It's not preferable on the manufacturing side, but it can be done. All right, got a couple minutes left. Let's see. Is there a consistent relationship between layer count and yield? Is it more linear, or is there a tipping point? So yes, there is a correlation between layer count and yield. As the layer count increases, the yield goes down. It is fairly linear, probably to about 14 or 16 layers, and then above 20, it definitely takes on a different slope, or more of a exponential growth above 20 layers. But also a lot of that depends on what the consistency of those layers are, what the thickness of the dielectrics are, the registration tolerances, etc. So that's there. Can you perform thieving cross hatches yourself from our Gerbers to deal with low pressure areas? Yes, we can, if we're given permission by the customer. Sometimes they don't want anything added to the artwork inside of the image. But if that's something that isn't going to impact your design, and as one of your print notes, you say, adding copper thieving or copper fill is acceptable, then we can definitely do that during the CAM process. All right, one more, and then I think we're going to be out of time. Is a 3-layer board a real thing? Yes. It's built a lot like a 4-layer board, but typically we just etch one of the copper layers completely blank, and that leaves you 3 layers. So it's definitely a real thing. Odd layers are very similar, except, like I said, we're just etching one of the layers on those copper pairs blank. All right, everyone, I think we're out of time for today. Thank you all for attending. I had a great time. Hopefully you guys learned something. I know that we'll be sending out this slide deck to all of the people that registered for this here in the next day or so. So be looking for that. And if there's any other questions, our phone number or our support emails are right there on the slide. Feel free to reach out. And we'll see you again next month for our webinar topic yet to be determined. All right. Have a great day, everyone. And let me know if you have any questions.